Alright, now, for those of you who are watching at home, apart from all you guys that are here, alright, this is really for your benefit. So, what we're going to do, and I'm going to follow through the textbook pretty much, so that whenever we record a lesson, you know what page I'm talking about and what section we're talking about. So, in the textbook that we're using, it's 2.3, Optimising Production, alright? So maybe if you guys can have your textbook open at the same page, this is the sort of stuff that we'll be doing, alright, when we record the lesson. Alright, so 2.3, we've just spent a lot of time going through these things. We've just done heaps of questions on equilibrium, we've talked about reaction rate, and we also sort of talked about enthalpy at the same time as what we did reaction rate. And everyone was pretty okay with that. We need to do a lot more questions on equilibrium, and I've already set those for you in the actual sector anyway, in the lessons. And the ones we're talking about, by the way, are these additional ones. Alright, so I've actually set those for you as well, extra practice questions, just to make sure you've got a hand on that. Because if you don't know that, this is going to get way more complex. So that's the foundation, alright, before we actually apply it in an industrial sense. Alright, when we talk about industrial chemistry, when I went to uni many years ago, I started doing a course called Chemical Engineering, and it wasn't long into the course that I realised that it wasn't as exciting as what I thought. It was chemistry, but it dealt with one thing only, and it was, for example, you would spend years, months designing a plant, like a manufacturing plant, to produce ammonia, but that was the only reaction that you were really focused on. So it only had one reaction at the end of the day, but it was how do I maximise that reaction if I wanted to produce thousands of tonnes of ammonia to use in other industrial processes. And so I jumped out of that because it was okay, all right, but I found that it was basically didn't really interest me, all right. I wanted more wide stuff to deal with, so I was more looking at lab stuff, teaching. Anyway, that's something for you to consider. So, chemical engineering, this is the sort of stuff we're working on now if you go on and do chemical engineering. Alright, flowcharts. Now, optimising production means how do I maximise production? Because currently, with the COVID situation, some production, you know, probably would have stopped. Okay? However, when it starts up again, I can guarantee that people know that the more stuff that I can make, whatever the stuff is, in the shortest amount of time, with the least amount of cost, means the most profit that I have. So this is what we're talking about. We're talking about how do I make chemicals and make some profit at the end of the day. And it's really about how much I can make, isn't it? So the more I make, the more money I make. If I can sell it, that is. Alright? And so in your books, you'll see these flowcharts, and the flowcharts will be for various industrial processes, and they're all a little bit different. I haven't put in all the steps, but basically they've got some sort of a beginning step, and they've got some sort of a final step. There are reactants that are occurring at the beginning, and at the end, you hopefully end up with a product. Okay? So it's an equilibrium reaction at the end of the day, that's all it is, but there are a number of steps in industrial process to get to products. It's not just one step. Okay? And we'll see that later on when we look at the contact process and the Haber process over the next few lessons. Now, to make this simple, we're going to try and make something really complex simple, break it down to the basics, is that you'll have this flowchart in this sort of a section here, and there's an example in your books that you'll see. The way to look at it is this. First of all, they talk about three basic things that are involved in all flowcharts for industrial processes. Raw materials, byproducts, and waste products. And of course, the product I should have mentioned as well, because the product is what you are making. I thought that was obvious, so I didn't even put it in. So that is obviously the product, and that won't be coming into the system. The product will be going out of the system. To differentiate between product and byproduct, I'll talk about that one in a minute. So raw materials is things that I can go and get in order to start off a process. So air is a typical raw material, okay? Crude oil that I would get from the ground, from an oil well, is a raw material, okay? So anything that I don't have to make, that I can get from the environment, is a raw material. iron ore is a raw material in the production of iron. Everyone got that? So raw materials are normally things that you see at the beginning of a flowchart, and raw materials are things that go in. I'm trying to explain that that's what it is. So raw materials are going in. They might go in from the beginning. There might be raw materials that will step in at various points in the process. And that's hard to interpret from flowcharts. That's not my favourite part of the course. However, the general rule is any arrow pointing in is normally a raw material. Okay? Now, this is hard. The next ones are byproducts. And this is where I get confused in some questions as well. Byproducts. At various points in the manufacturing process, you'll see that there will be chemicals that are produced. For example, I might end up with a product called water, okay, being produced at some step of the reaction. Somewhere else, the reaction will need water in order to carry on the reaction. And so water is not a waste product. Water becomes a byproduct because it's used again in the system. It's cycled back into the system again. In lots of reactions, they use the heat as a byproduct. Not strictly correct, but they use the heat in the system further down the reaction. They capture the heat, all right, with heat exchangers, and they use it further down in the system, wherever that is. Okay, just tell Enzo not to come in when I'm recording. All right, now, so we've got water out, water in. Okay, for the system. The next thing is waste products. Okay, waste products are chemicals that don't go back into the system. They have no further use. And there's a fine line between byproducts and waste products, okay, as well. That's okay. So there's a byproduct, so there's a fine line between these two chemicals, okay? And again, you've really got to look at the flow chart and see, well, if I've said product X is a waste product, then you've got to go and see, well, does X appear anywhere else in the system? If it does, X is probably a byproduct and not a waste product. Okay? So interpreting these is not easy. Never is. Okay? The example that they give you on page 199 using our resource, okay, if you can flip over and have a look at that one. Okay, you can see that there's arrows going into the system and arrows going out. So water would be a raw material. Air is a raw material. Sulfuric acid comes into the system. Sulfur dioxide goes out of the system. All right? But you can see sulfur dioxide is used in the system again. Metal residues, you know, only go out. So that would be easy. The metal residues from that process there to produce zinc, that would be a waste product because they're not coming in anywhere else. Okay? And then sort of that flow chart there is okay to understand, but you'll see others that aren't so easy. Okay, now, so we're on about products. We also talk now about the yield for a reaction. We won't get to do much in terms of yield. We'll do an organic preparation later in the year, okay? And you're going to measure and I think that's when we're going to do an ester. We'll do that as a bit of a mock-up. So you're going to measure the mass of one of your esters. All right, it could be, say, ethanol, and we might be using the ethanol to make maybe ethyl ethanolate as an ester product. And so you're going to measure the mass of one of your reactants, and then you're going to measure the mass of the product you get at the end of the process, and then you're going to work out the yield. Okay? Now, here's our little example that we sort of mocked up fairly quickly on the board. Now, that's supposed to say assuming 100%. So, the formula for yield simply says how much or how efficient has my reaction been. That's all it means. So, am I getting lots of product or am I getting not much product? So, percent yield is the actual yield. I've given this a number. I said, let's assume we're making ammonia, which is one of the processes we'll talk about in a minute. Let's assume we're making ammonia. We end up with 5 grams. This is only in a lab, pretty small scale. This would be like in tonnes in the real world. Okay? So we end up with 5 grams, and we start off with nitrogen 10 grams. I'm giving that to you. Here we go, got nitrogen 10 grams. We've got unlimited H2, which means H2 is the excess. So in this case here, I'm telling you that the nitrogen is the limiting reagent, so you've got to keep that in your head as well. Limiting excess comes into these reactions as well. We did the calculation, we worked out, alright, so theoretically, if I were to get 100% yield, if that reaction went all the way to the right, we know it doesn't because it's in equilibrium, then from that 10 grams, I really should have yielded 12.2 grams, okay, doing my calculation. That's what the reaction should have given me if the reaction went to completion. But it doesn't because it's in equilibrium. Okay? So we end up with 5. We actually ended up with 5. So when we actually put it into an equation, it becomes the actual yield. This is what I recorded at the end of the experiment. Okay, I measured it. And this is what I calculated, 40.9%. What do you think? Is that a good yield or is that a bad yield? It's pretty bad. It's less than 50% of, way less than 50% actually. Okay, so it's extremely poor yield. However, now we look at how can we maximise the yield. Believe it or not, 40% for this product is pretty good for ammonia. Okay, so now when we look at maximising the actual products in an industrial sense, we've got to think of heat, reaction rate and equilibrium all together now. We're going to maximise all those things. But some things are going to be contradictory, and I'll talk about that right now. So we're going to work through this one real time. So I'm not going to give you the answer for this, but I'm just going to work this one together. I'm going to ask you what temperature conditions would favour the production of ammonia, and I'm going to ask you what other conditions, what pressure would favour production of ammonia. So what temperature and what pressure? Let's work on temperature first, okay? So if I'm using temperature as an indication, okay, to favour ammonia, I want it to go to the right-hand side. How do I tackle that one in terms of Le Chatelier's principle? Okay.
Identify which way is exothermic and which way is endothermic.
Good. Okay, so which way is exo for this reaction?
To the right.
Okay, so to the right is an exothermic reaction, to the left is an endothermic reaction. So therefore, what temperature would favour equilibrium to the right? Okay.
Low temperature.
Low temperature. Okay, so what we're saying straight away is that from what you know already, low temperature would mean the concentration of NH3 would be favourable, according to Le Chatelier's principle. This is how we argue it. Okay? Everyone happy with that? Cool? Yep. Alright, now, that's temperature. Let's look at it from a pressure perspective. Okay, if we look at pressure, how do we tackle a pressure scenario? Finn?
Which side is more moles?
Which side's got the more moles of gas? Just look at that first, don't we? So we've got 3, left-hand side has got 4 moles of gas, the right-hand side has got 2 moles of gas. So what's going to favour the right-hand side? Low pressure or high pressure? Which one is it? We want least moles. So if I have, let's look at each one. So if I say high pressure, which side is the reaction going to move towards to reduce the pressure?
The right side.
The right side, yeah. I can pick the right one first. Alright, so this would say that high pressure will favour the reaction to the right. So therefore the concentration of ammonia is going to be favoured under those conditions. Okay? Now, that's what your knowledge tells you, correct? That's what the theory is telling you right now, based on your current knowledge. So now what we do is this. We go out and we'll look at the contact process, and I've got some videos coming up on the contact process. Haber process. This is the Haber process for ammonia. And in reality, we now have a conflict. Okay, and I'll show you where the issues are with this one. And all the questions sort of are on the same sort of a pattern in how you tackle them. So, what does this tell you about the rate of the reaction? What do you know about rate and low temperature? Anyone? Harrison? Slows it down. So, we've got this balancing act now. Okay, so we've got what we just said, low temperature favours ammonia. The problem is that we know about reaction rate. Okay, we know about collision theory, so a low temperature means, okay, I'll get a really good yield, but have I got a year to wait to get that yield? Can I make ammonia and get a fantastic yield, but sit back for 12 months and let the reaction take its time? No. Okay? So, when we look at this, alright, temperature is one of those things that I now have to look at a balance of a less yield, lower yield, but a faster rate. Now the only way you can do that, okay, is to carry out a whole lot of reactions. And they've done that. In the book, you'll see graphs of the temperature versus the yield for the production of ammonia. We'll come up to that in the next few lessons, okay? Or you can flip over a few pages. Let's have a look. If we flip over a few pages, somewhere, where is it? Not there. Okay, so if you look on page 205, can you see the different temperatures there and how it affects the yield? Okay, there's 550, 500, 450, 400, 350. Now, you can see that as the temperature goes down, like at 350, the yield is higher. Okay? So the yield is actually higher at 350. However, what they've worked out through a whole series of reactions is that they've worked out that it's a compromise. They've worked out that 400 degrees Celsius is a compromise between rate and yield. Okay, they don't do this overnight. It's done in a lab. All right, many different reactions. How can I maximise my yield so I get enough produced really quickly, but it's not going to take me the millennium to do it. Okay, because I have to get the product produced quickly. And you can imagine what people are doing right now in terms of making the hand sanitizer as well. All right, so that's not so bad. But if we are taking, for example, anything that's going to be fermented, they might want to increase the fermentation reaction, but they also want to actually distill it off to get the ethanol to go into the hand sanitizer. But they would want to maximise the production of ethanol in whatever system they are using. Okay, because they need a lot of it, and they need to get it quickly. So they might be whacking up the temperature to increase the quantity that they're going to get, but sacrificing the yield, maybe, because they want it quicker. Everyone got the idea about what we mean temperature, yield? Okay, pressure. If you look at this one over here, what do they do it at? What pressure? Okay, here it is. They do it at 100 to 200 atmospheres pressure. 100 to 200 atmospheres pressure. So this is not high pressure, this is extreme pressure. Okay, extreme. So we're now experiencing 1 atmosphere pressure. So within an industrial process, you could imagine they'd have to have some fairly special equipment, okay, in order to simulate that pressure for that reaction. That's a really high pressure. Why do you think they've got such a high pressure? Think about it. Why do you think they've gone crazy with the pressure? Harrison?
To speed up the reaction.
No, it's not going to speed it up because this is the rate. The temperature determines the rate. But why have they overcompensated for the pressure, Jack?
To increase the concentration of ammonia.
Yeah. So they know that they're going to get a crappy result up here, so the temperature is going to make it go that way, in theory. But what they're thinking is, oh, wait a minute, I still got one little trick up my sleeve. Let's increase the pressure. But let's not increase it to 2 or 3 atmosphere. Let's really go max. Let's go the highest pressure we can, and still trying to be safe, and also, by the way, still trying to do it with basically cost efficient. because that means the industrial plant that would be used to make ammonia would not be something you can go and get at Bunnings. Yeah? It would have very, very special engineering requirements to meet that really high pressure. But of course they've done their sums, okay? Ammonia must be worth a fair bit of money, and so they're going to throw the money in to build up the plant, whatever the industrial process is for it, knowing that they're going to get a return, okay, with their ammonia at the end. And of course, maximising the yield. So that's what this is on about. So the whole section on industrial processes, and we're going to look at two of them. We just touched on one then, which is the Haber process. Contact process, Haber process, and you'll be given not those in a test or exam, because you already know what the answer is for those, but you'll be given other scenarios of industrial processes and asked to argue the same way. Okay, so you might have an example just like that, and then you've got to argue, alright, temperature tells me this, but pressure tells me that, it's a compromise, what would you suggest would give me the highest yield? Okay, and that's just our intro to industrial process. That's actually really most of what we're going to do, apart from the contact process, okay, which is producing sulfuric acid. And we're going to leave it at that.